Welcome to this another lecture of Introduction to the Reactor Design related to the polymer reaction engineering. Earlier we had a discussion about the different parameters associated with the reactor design. We discussed about the different type of reactors. We discussed about the different component involved in the reactor design. Now here again we will continue this concept of reactor design with the help of rate equation. Now we had discussion about the importance of the rate equation in the previous lecture and what triggers the importance of this rate reaction into the designing factor of the reactors, especially attributed to the polymer reactor. Just a brief thing which I would like to pose before you. This thing is related to the sensitivity of this particular polymer products. You see that in the previous lectures we always emphasizing the fact that because of the sensitive approach of molecular weight distribution and in situ its influence to the property of the polymer being produced. So, we need to have a very close look to the designing aspect of these reactors. A slight variation in any kind of approaches may create a severe economic loss to the industry, severe economic loss to the nation. So, that is why these closed look parameters, whether they are catalytic or non-catalytic, whether they are homogeneous or non-homogeneous, whether they are temperature dependent, exothermic reactions, etc. So, we need to give a proper importance related to the these parameters. So, we will continue this rate equation approach in this chapter 2 with the rate laws, concept of rate laws, etc. So, in addition to the previous discussion, let us say that another equation for every moles of a reactant A, there is B A moles of reactant B consumed to form this much of moles of a product and this much moles of product D. So, the rate of disappearance of reactant A, because A and B both are consumed in due course of time within the reactor. So, the rate of disappearance, and that is why we put negative sign before this. So, the rate of disappearance of both reactant A and B and the rate of formation, it carries the positive sign. So, both C and D both are being formed in due course of time. So, let us say that again go back to the previous equation. So, A plus B upon A B, C upon A C plus D upon A. Now, so rate of a reaction you can always write RB. Remember, negative sign we have put just because the both A and B, they are consuming themselves in the reaction mass. This is equal to A upon C So, this is the rate of equation. So, by this way we are already discussed and we have given a clue about the importance of a rate equation. Now, come to the rate law. As I discussed that rate law is the algebraic equation which relates the concentration term with rate of a reaction, and sometimes they are also, it is also called the kinetic expressions. Now, in the rate equation, say minus RA, which we are representing over here, is a function of a temperature and the concentration term, reacting material and type of catalyst as at a point of a reactor. Maybe your reactor, or maybe sometimes it is referred as the contacting pattern, etc. So, here the negative sign, as I told you, that represents the decomposition or consumption of a reactant A in the chemical reaction, which can be determined by the experimental observations. So, according to rate law, the rate is directly proportional to the reactant concentration in the reactor available to react. Now, if a chemical reaction proceeds with the reactant A and the decomposed into the product R, then let us say that this is my general equation. So, in that case, minus Ra is a function of temperature and concentration, or sometimes referred as minus Ra is equal to Kca to the power n, or it is represented as this is the concentration dependent term, and this one is your temperature dependent term. So, this gives you a generalized equation and generalized concept of rate law. Now, here K naught in this particular equation, again I am repeating this equation over here for the convenience, minus Ra is equal to Kca. Now, here K naught E, this one represents the temperature dependent term in the rate law, and this Ca concentration of reactant A, and it is represented in mole per liter. K is the specific rate constant having the unit of mole per liter to the power 1 minus n second. Now, K naught, this represents the frequency or a pre-exponential factor having the same unit as that of a specific rate constant K. Now, E here, E is the activation energy and having the unit of joule per mole. Now, T here, this is the temperature usually in Kelvin, and N represents the order of a chemical reaction. Now, let us have a look about the concentration dependent terms. Now, the concentration term, they are used in the rate equation. It depends upon various factors. Now, one factor is that the single or a multiple reaction. So, when raw material reacts to form a product, then it is easy to decide whether the single reaction or multiple reaction exist. This only after the examination of the stoichiometry at more than one temperature. So, the governing factor is your stoichiometry, that is at the multiple temperature profile. There may be certain multiple reactions. Now, for multiple reactions, there is a need of more than one stoichiometric equation and more than one kinetic expressions. That is, sometimes you may have a series of a reaction, sometimes parallel reaction, sometimes series parallel reactions, or sometimes a very complex reaction in nature. Now, here you can have a look about the series of series reaction. Now, here these are the parallel reactions. Now, you see that the arrow parallelly, these things are moving on opposite direction, and here A is converting into the B and then subsequently C. So, this one is the series one and this one is the parallel one. Now, again come back to the single reaction. For a single reaction, there is a need of a single stoichiometric equation and single rate equation. Now, these two things, they represent the progress of any kind of a reaction. Now, here you can see that this particular equation, this is the reactant, both A and B are the reactants, and their stoichiometric numbers are correspondingly in the small letters. The K1 is the rate constant, and similarly C and D both are the products, their corresponding stoichiometric numbers are C and D. Now, let us have a look about the elementary and the non-elementary reactions. Now, before we go into the detail, let us have a look about the elementary reaction. So, when there is a direct relation of stoichiometry to rate equation, or stoichiometric coefficients sometimes are same as the power raised to the concentration term in the rate law, then this is termed as the elementary reaction. Now, just for the sake of an example, this is the example of the elementary reaction. Now, the rate equation of the decomposition of reactant A is given by minus Ra is equal to K Ca Cv. So, this is purely based on this particular reaction. Now, the concept of non-elementary reaction is say that when there is no direct relation in between the stoichiometry and the rate equation, or sometimes the stoichiometric coefficients, they are not same to the power raised to the corresponding reactant concentration, terms used in the rate law, then the reaction is said to be the non-elementary reaction. So, we should need, in this case, we should need of a series of elementary reaction to solve any kind of non-elementary reaction. Now, this is a very complex type of scenario when we need to solve these non-elementary reactions. Now, in this case, we need to assume to be a series of elementary reaction, those who are occurring, and negligible amount of intermediates that are formed with a short time of period. So, sometimes you need to negate various aspects attributed to this particular approach. Let us have an example of twice N2O is converting into 2N2 plus O2. So, the rate of above non-elementary reaction you can write as minus R N2O, because this is being consumed in due course of time, is equal to K C N2O, that is the concentration of this N2O upon 1 plus K to the power 1 CO2. So, this is the concentration of oxygen. Now, another important point in the reactor design is the molecularity. Now, it can be defined as the number of reactant molecules, atoms or ions, those who are participating in a balanced chemical reaction. So, these number of reactant molecules, they are referred as the molecularity of the reaction. Now, this approach is based on the collision theory. Now, it is the whole number such as 1, 2 or 3. Hence, the reaction is said to be the monomolecular, dimolecular or termomolecular reaction. That depends on the number of molecules participating in the collision. It cannot be in the fraction, because it is quite obvious that partial collision may not be feasible, may not be possible. So, it cannot be in fraction, as no spaces within the fractional number of molecules are used in chemical reaction. So, molecularity is only used in the elementary reaction. Sometimes people may refer as a unimolecular. Now, the arrangement of a single molecule to produce one or more molecules of product is an elementary system. For example, the decomposition of radioactive material into more than one product, such as a radioactive decay of say uranium-238 into thorium and helium by emission of a single alpha particle. This is the unimolecular. There are certain bimolecular reactions. Now, the arrangement of two molecules in the reactant to produce the product of reaction, this may consist of two chemically different molecule or similar molecules. For example, this one 2N2O is producing 2N2 plus O2. Another arrangement is called the termomolecule. This arrangement, there are three different molecules in the chemical reaction to give the different products. Next part is related to the order of reaction. This particular concept is again very useful for the determination or designing of determination of various parameters associated with the reactor design or designing of the reactor. So, here this is the sum of the power raised to the concentration term in the rate law is said to be the order of reaction. The overall order of a reaction, it can be a fraction, say 0.5, 3 by 2, 5 by 3 up to n, or sometimes it may be a whole number, 0th order reaction, first order, second order, third order, and so on and so on. Now, if let us take an example that the following reaction take place where reactant A and B both are reacting together to form C and D. Now, here this reaction is represented with their corresponding stoichiometric numbers. Now, according to rate law, you can represent this as a minus Ra is equal to Ka C to the power x Ca to the power x and Cb to the power y. Now, in the rate law, x is the order with respect to the reactant A and y is the order with respect to the reactant B, and the overall order of the reactant is the sum of orders with respect to A and B. So, sometimes you may refer that the overall order of that particular reaction is represented as n is equal to x plus y. Now, the overall order of the reaction for the single reactant system is n, then you can write the rate law, that is the single reactant. Now, rate law, you can write minus Ra, as negative sign is there because A is being consumed, is equal to Ka Ca to the power n. Now, if order say n is equal to 0, then in that case you can write minus Ra is equal to Ka, that is a 0th order reaction. Now, if order of the reaction is 1, then you can write minus Ra is equal to Ka Ca. Now, if order is 2, then you can write minus Ra Ka Ca 2. So, this represents the order of reaction. Now, in this particular segment, we discussed about the rate law, we discussed about the rate equation, we had a brief discussion about the order of the reaction, and all these parameters, all these things, all these theories are extremely important for the designing of a reactor. So, we are proceeding towards the designing of a reactor with the help of these different variables which are closely related to the design aspect. If you wish, you can have these references for your future reference. Thank you very much.